Hi everyone, I'm Yikun, and on behalf of our team, I want to thank all the organizers for organizing this challenge and providing this precious experience. And this is really a joint teamwork with Zhehua Wang, Stephen Yang, and Professor Ambut Tavori, and we are from Department of Statistics, University of Michigan. So here is a brief outline, and I will skip the background part because it's introduced clearly, and I will discuss more detail about our methodology and finally our conclusion. So here is the data set, and our task is to build a model to find the metric between two mixtures and finally do a discrimination test based on the perceptual score. So one thing may immediately come to your mind is that till now we still haven't get any olfactory related information or the perceptual information or features. So the first step in our pipeline is to actually predict the perceptual embedding and use it as upstream information for our further steps. So let's take smiles of caffeine molecule as an example. So smiles is like a text-based annotation systems to represent the chemical structure. And on the one hand, we can transform the smiles to a 2D molecular graph and then feed this topological information and also all the nodes embeddings and the edge embeddings to a graph neural network layer and get the perceptual embeddings for single molecules. And on the other hand, we can use these smiles to get the Dragon chemoinformatic features. And since Dragon software is not accessible anymore, we can easily substitute it with Mordred or Morgan features. And then we take it as an input to a random forest module to predict the intensity. And for the dataset size, the training set has 500 mixture pairs, and both for the leaderboard and test sets, there consists of around 46 molecule mixture pairs. And let's divide this pipeline to two parts. So the first part is about the molecular graph part. And for this model, we actually use a pre-trained model from this paper called the principal Odor map. And we use the open source version of it called OpenPalm. And the performance on UROC is pretty close. And the Goose and Nightingale dataset is introduced by Joe before. So it consists of around 5,000 molecule samples and 138 labels. Basically, they are all order descriptors, and the task here is multi-label classification. So for a single molecule, it can have a multiple order descriptor label or value. And for the second part, for the intensity part, we are actually motivated by the last DREAM challenge, so held in 2015. And back then, the state of the art model was called random forest, and I think it's also due to the data limitation because it's around 300 molecules. And the data set we use is Keiner volatile data sets around 300 samples and 19 order descriptors, presentness, and also intensity. So the only thing we care about now is for the intensity part, and for the order descriptors is based on multi-label classification. And for the presentness and the intensity, we are using regression value. So since we only care about the intensity, so this model is solely based optimized on the intensity performance. And we did make some modifications based on these two parts, but not based on the model, but more on the data part, since data is more likely to be the bottleneck. And for the first model, we weighted the molecules in the intersection of the pre-trained data and computation data more heavily. And we also merged the test data set to provide a larger training set and for better upstream information. And for the second model, we merged the leaderboard and test set to get a better training result for the intensity value. Okay, this is just a brief introduction of the graph neural network. And so the first step is to transform a molecule to a graph and then feed it to a graph neural network layers. And you can see the information is aggregated from its nearby neighborhood or nearby items. And we can do this graph to vector operation and finally take it as an input to a neural network for the final prediction. And we can also get the graph embeddings intermediately and use it as an upstream information. Okay, so till now we can get the information for a single molecule, and the next step is to transform the embeddings of single molecules to embeddings of mixtures. So here we apply a softmax transformation to normalize the intensities, and where WIs are the normalized weights, and the final mixture embedding is weighted sum of the perceptual embeddings. And intuitively, we can know that if a single molecule has higher intensity, we should assign higher weights during its mixture transformation, but we don't know how much it matters. So we introduce a temperature parameter tau to control the smoothness of the softmax. So a lower temperature makes the weights sharper, focusing on larger values, while a higher temperature is closer to the average. And this really helps us to adjust the influence of each molecule in the mixture. And next step is to transform the embedding of mixtures to the distance value. So after we do the softmax transformation, we can get the embedding for mixture pairs, and we take the square loss of these mixture pairs to the cat boost module, and finally predict the perceptual distance through a metric learning approach. So one thing you may notice here is that this pipeline really consists of multi-steps. But so the first step is to get the embeddings of mixtures, and the second step is to transform the embeddings of the mixtures to distance. But we cannot evaluate during the intermediate process. So we did a combined grid search based on the temperature tau and also on the NS meter of cat boost, and also a few other hyperparameters to get the best result. Okay, so for cat boost, it may be not familiar compared to XGBoost or RSGDREAM or something like random forest. So the thing here is that cat boost is using symmetric trees. So basically trees where the same splitting criterion is applied across all nodes at the same depth, and it provides efficient computation and also fast prediction. Also, since the model is simpler and the tree is more regular, so it's kind of the regularization effect to prevent overfitting. And here are a few results based on the final metric learning part. So we try several methods and approaches, and we all kept the same setting, which used the tenfold cross-validation, and finally used the ensemble result of these 10 models. And you can see that some of the approaches are actually overfitting on the valid set we split off from the training set. And compared to other models, cat boost doesn't suffer seriously from this problem. And here are some key insights from the small data. So here we relied heavily on other pre-trained models, pre-trained on other tasks and other data sets. And also we seriously consider data augmentation here. So we try to substitute in a single molecule in a mixture with its nearest neighbor, and it's defined based on the pre-trained or the predicted graph neural network embeddings. But this approach did not yield improvements. And we also try to keep these models really simple, because small data led us to keep the models and featureization straightforward. So you may notice that we didn't use any deep learning methods from scratch. We kind of tried to replace the final metric learning part to like a Siamese neural network. So basically, the motivation is from computer vision to identify. For example, if we give the model two portraits, and see the model whether can identify if this comes from the same person. So it's really similar to this perceptual distance problem, but it doesn't work well because of the data limitation. And also for the featureization, we also keep this method straightforward. We used the softmax transformation and also a square loss, and we also substitute these two parts with mixture attention, but it doesn't work well. And finally, for the regularization part, cat boosting integrates strong regularization techniques, which helps us prevent overfitting more effectively than other boosting and bagging methods. And perhaps looking to the future, we are thinking about, as the larger the data set become available, we will explore more pre-trained models, particularly focusing on odor receptor modeling. For example, modeling the relationship between the odor receptor and the molecule, like the underlying mechanism. And also deep learning, especially with attention mechanisms, will be leveraged to better capture the relationship between sets and create more sophisticated embeddings. And finally, with more data, advanced data augmentation or data curation techniques will be further explored to enhance the model performance and generalizability. And thanks to all my teammates for contributing great ideas and working hard, and thanks to my advisor, Professor Tavori, for guiding me and encouraging me on the way. And also thanks for all the organizers again. Yeah.
I think we have time for a couple of questions, if there are. I do have a question for you. Sorry, and maybe I missed, but what do you do with the embeddings for each of the molecules? Do you just concatenate them, or?
You mean from the embeddings of single molecules to the embedding of mixtures?
Yeah.
Oh, we just did a softmax transformation mentioned.
Oh, softmax, okay.
Yeah, here.
Okay, so you do just this sum. Okay.
Yeah, we just assume higher weight to those molecules who have higher intensity. Yeah.
Okay. Sorry, I missed that. Sorry. Yeah. And second question, just from the organizer point of view, who decided to participate in the challenge? How did you find about it?
Oh, actually, I think I was involved in machine affection study since last year. I entered master study, but I'm not really sure how I gonna improve it. But from this challenge, we are kind of seeing some of the interesting direction. And my advisor noticed this challenge through one of his peers, but I forgot his name. Yeah.
Yeah, because we have Yuan Fang from the University of Michigan. Is a champion of DREAM, and her team has won many challenges, and so we were surprised and happily surprised to see another team from the University of Michigan perform well and participate into this. So,
oh yeah, I know. Like for the last DREAM affection challenge, they won the
exactly.
Oh
exactly,
yeah,
exactly. So,
hey, great talk. So, can you tell me a little bit about how you calculated the intensity? So, are you getting one value of intensity for each molecule, or do you worry about the concentration of them in the particular mixtures at all?
Actually, I think since the dataset doesn't provide the concentration value, we just use the random forest trained on the last GMO factory training set, and we assign all the concentration of a single mixture are the same. So yeah, since there is no information here.
Got it. And if you remove that, did you check and make sure that actually improves the prediction?
Yeah.
To include it? It does.
Yeah.
Awesome. Thanks.